the potential at point B, which is this point, is supposed to be right on the y-axis, and the same two charges at the bottom. What do you think it is? All at once. 0, because I'm in the exact same distance from both of the charges. So both of those terms on the previous slide are going to be equal, just one positive and one negative. So at that point, I get 0 potential. Now, you could imagine for a situation like this where I have two charges, I could ask you to find the potential at any point, right? I could say, hey, what's the potential right here? What's the potential right there? What's the potential right here? What's the potential right there? Right here, I could sign like 1,000 million problems, right? If I wanted to. Like, practice if you want to. Just pick some random place that's some distance from the two charges and make sure you understand how to calculate the potential. You should also be able to take two charges and find the force on a third charge somewhere else. You should be able to take two charges and find the electric field at some other point. These are all things that we've done in these first three chapters. Electric field, electric force, and potential from point charges, okay? We're gonna do an example later that's just like that, all right? So moving on, 4 point charges are arranged at the corners of a square. The two left ones are negative, the two right ones are positive. Find the electric field and the potential at the middle on that black dot. And you can see our answers are not exact, it's just 0 or not 0 for both of them. The electric field and the potential at the center. What happened here exactly? I feel like something occurred here today that like either someone was in trouble and they were forced to sit with this little desk chair thing. Maybe someone had lunch here. I don't know. I kind of want to lecture from this position for the rest of the class. There we go. This is kind of fun. Y'all think about that while I'm over here doing my own thing. Can't help but want to turn around. Let's take them one at a time. Potential at the center of the square. 0 or not? That's good. Nice work. So the two answers are either 0 or not. So say the word 0 or not, whatever your answer is. Go. 0. It sounded more like 0, right? So our answers are either that one or that one. And again, that point at the middle is equidistant from two positive and two negative charges. It should add to give me 0. But what about the electric field? Imagine what would happen if I drop a positive charge at that point. Will it feel a force or will it not? Sure seems like it might feel a force, right? You can imagine it's going to be repelled by both of these, and it's going to be drawn to both of those, right? It's going to feel a force toward the left, at least roughly speaking. So the potential here is 0, but the electric field there has some value that points to the left, because I know a positive charge would feel a force in that direction. So our overall answer is this. There is an electric field at that point, but there's no potential. How's that possible? One second, I'm going to change slides and see if there's something here that might help. Going back to, which one? Maybe this one would help. Take a look at that right diagram. Remember we talked about this being like a big mountain that's coming out? And over here, this negative charge represents a negative, like a hole of potential, right? Well, right in the middle, you would have a potential of 0. Agreed? It's kind of like, that's kind of like ground level. Here I have a mountain, here I have a valley. Right in the middle is like exactly 0, not positive or negative. But right in the middle, there is an electric field because something's going to want to go from high down to the low point, okay? There's still an electric field in the middle because there's a slope in the potential, where the negative slope of the potential is the electric field. So you can almost imagine this, like if I were to flip this sort of sideways like this, like it's going something like this. I'm going from one peak in the potential that's positive down to a valley that's negative. There's a point in the middle that's zero, but the potential is changing and has a slope through that point. If there is a slope and the potential is changing, well then there is an electric field, okay? If you're trying to think about how the electric field and potential relate, like try to get some of this three-dimensional figure stuff in your head. Try to relate it back to that. Imagine potential as these mountains and valleys. And I think it helps a little bit trying to understand the electric field. Maybe it does, maybe it doesn't, who knows? So back to this one. Electric field is not zero, it exists. The potential though is zero. Yeah.
Is the force being exerted by both the positive charge and the negative charge the same?
The force being exerted by both.
Like if we see it in two separate systems.
Yes, but it's also dependent on the charge that's feeling the force. So a given charge would feel the same force from both an equal positive and negative charge, just in opposite directions. Yep. Okay. Yeah.
Even though that it's like neutral, if they're both like giving off the same, it's still like the forces they feel. That's why we have to answer it as like not equal to zero.
As far as in this problem? Yeah, if there is a force, then there is an electric field. And there will be a force if you can imagine repulsion and attraction being something that's happening at that point. Okay? There's one new thing here on the slide. One new thing. There's going to be something a little new later, but actually we've already kind of talked about it. So electric potential from point charges is what we just finished. We just use K, Q over R if I have a point charge. But sometimes I have too many charges to count, just like before, and we express that as a distribution of charges, just imagining there's like infinite numbers of little charges that are all sort of packed together. We're going to do something kind of like that with a bunch of charges distributed in a ring, okay? And again, it's going to work the exact same way. We're going to imagine there's a little bit of charge in a little bit of that ring, and then we're going to see what the potential is over at some point from that little bit, and then add up the contribution from all the little pieces of the ring that each contain some charge. The thing is, this time I'm not going to think about like, oh, there's like a vector and some of the components maybe cancel out and some don't. I don't have to think about that. I literally get to just use the integral to just add it up because it's a scalar, which makes life a lot easier. So we're going to express this in an integral form to allow us to do this. So I could write V as K or 1 over 4 pi epsilon naught times the integral of dq over R. And we'll call this the integral form of the exact same equation. It's just now we're breaking up the charge into little segments of charge. So if I want to use that equation with this example, this ring of charge, watch how quickly we arrive at an answer. It's kind of ridiculous. So first of all, this R that's there, if I'm trying to find the potential at this point that's like some distance x right away from the middle of the ring, well then over to any point on the ring, the distance R is this hypotenuse. And that value is constant, okay? No matter where I go on this ring, the length of that hypotenuse is exactly the same, and it's the square root of x squared plus r squared, the radius. It's going to be a constant value though. So I can go ahead and pull that out of the integral. So I've got k over r dq. And then we can express r as what they have there, the square root of x squared plus r squared. So I've got k over the square root of x squared plus r squared, integral dq. And we're basically done, believe it or not. If I'm just doing the integral of all the little pieces of charge, what is all the little pieces added up? it's just Q. So this is KQ over the square root of X squared plus R squared. Wow, that was fast. That happened ridiculously fast. KQ over that distance. So what happens if I get very far away? Let me just see what happens. Very far away from this. In other words, if X is much greater than much. I can do this all day. You get the idea. Much greater than the radius. So instead of looking at some distance X, we're just going to let the X be way over here somewhere and try to find out what that would be. Well, I can take a look at this equation and say that now X squared is going to dwarf R squared by comparison. So essentially the R squared isn't even there anymore, and I just have the square root of X squared, which means that my potential becomes KQ over what? Just X, right? Where X is the distance away. Well, that looks a whole lot like this. We're just using X instead of R, but both are just a distance, which means if I get far enough away, this ring of charge looks like a point charge. And that fits, right? If something's a disk and I get far enough away from that, all I see is a point, okay? So this equation seems to fit with what we would expect from a great distance. And we're done with that. That wasn't too bad compared to some of the other calculus examples we've had, I don't think, okay? So let's jump over here, and I've got some other questions to give you. We talked about these equipotential lines and surfaces, and I drew this diagram, but we didn't actually talk about the problem that's sitting on that page. At which point, 1, 2, 3, 4, or 5 is an option, would the potential be equal to 0? Notice they drew a line down through here. This is an equipotential line. An equipotential line is a line on which all the potentials are the same, and all of those are equidistant from both the positive and the negative charge, which means all of them are going to have potential equal to 0, okay? What about this one? Which 2 points have the same potential? Don't think about this for too long. Which 2 lie on an equipotential line together? Looks a whole lot like C and E are both on this equipotential line that goes around closest. So our answer there is number 4. Okay, equipotential line once again. I already decided to skip the electric dipole stuff. Turns out we don't really need it for this class, so I'm going to jump over that, which brings me to the last 2 slides of this chapter, and then we're going to do some review stuff, all right? So electric field from electric potential. In other words, if you have the electric potential, which remember is a scalar, which remember is easier to calculate, we can go from there and calculate an electric field. If you have the potential, it's possible to go backwards and find the electric field without having to do all of the vector work. So you might remember we had an equation that kind of, let's see, it sort of looked like this. We said it was the change in potential over D. We had an equation that looked like that connected the two. We used that to say that the electric field is the negative slope of the potential. The electric field is the negative slope of the potential, and we used that idea together with our 3-dimensional diagrams to see how the potential is changing, and it had all of those little pink, purpley sort of lines on there that we said represented the electric field, and it was literally the slope of the potential. Well, I can re-express this equation just a little bit and write it as E sub L, where L is just some arbitrary direction. In other words, it's one of the components of the electric field. It's just instead of saying X, Y, or Z, I'm just saying that way, or maybe it's this way. I don't know. I'm not picking one of the directions. So I'm speaking really generally here. The component of the electric field in some arbitrary direction L is equal to the derivative of the potential with respect to that particular position. So again, we're dealing with the negative slope or the negative rate of change of potential in that particular direction, that L direction. So let's write down a couple of different things about what this means. First of all, this is mathematically known as the gradient of the potential in the L direction, in case you're familiar with that terminology. And it is the negative rate of change of the potential in the L direction. The negative rate of change of potential, which is defined as the gradient of the potential. So to put this in terminology that maybe you like a little bit better, we could find the X component of the electric field and the Y component and even a Z component if we had three-dimensional situations. We're finding the components of the electric field vector. We can use this particular equation in all three directions. So instead of some arbitrary L direction, we can write this in terms of X, Y, and Z, which we're a little bit more familiar with. Except if it's a function of maybe X, Y, and Z, I have to rewrite that as partial derivatives. So this would be the partial derivative of the potential with respect to X, and the partial derivative of potential with respect to Y, and negative the partial with respect to Z. And you might remember or may not that when you're doing a partial derivative, it just means you're going to take the derivative with respect to that one variable and hold the other ones constant. So your equation might have X's and Y's and Z's in there. Just pretend when we're dealing with X that anything with Y and Z is just a constant value, okay? And you're not having to worry about that at all. And let me do a quick example of this for you, okay? So let's say that we had something like this. The potential as a function of X, Y, and Z. Meaning maybe we have an equation that we could plug into the computer and get it to graph one of these pretty three-dimensional things that tells us what the potential is at every point in space. And maybe that function looks something like this. 2x squared plus 8y squared z, and who in the world knows what this looks like, plus 2z squared. Maybe you plug that in and get it to graph that in 3 dimensions for you. If we wanted to find Ex, well then we look at that function and again take the partial derivative of the whole thing with a negative sign with respect to x, making sure that anything that has a y and a z, we just pretend those are constant. So when I take that derivative, that's just a 0. We don't have to worry about it at all. So for this one, the derivative is going to be 4x, and we would throw a negative sign in front of it. So Ex is going to be minus 4x. That is the component of the electric field in the x direction. And Ey, we could do a similar thing. In this particular case, well, I have an x here. This one's going to be 0. We have a z over here, so this one's going to be 0. And we can pretend that the z in the middle is, again, just a constant. So in this case, we would have minus 16, and we could put the z in front to pretend it's a constant, times y, minus 16y. And the z component of the electric field would be expressed as minus 8y squared The first term is constant, so it's just 0. This one, we're pretending that the y squared is a constant, so everything is constant out in front of the z, so that's just minus 8y squared. And the last one would be minus 4z. Those would be the equations for the components of the electric field at all the points in x, y, and z space, okay? So you can do a lot of work in 3 dimensions if you know the function, and you can like very, very quickly get to the answers. And of course, if you wanted to say like, oh, well, what is the electric field vector at this point? Like maybe at the ordered pair 1, 1, 1, x equals 1, y equals 1, z equals 1. We'll just plug the numbers in, and it'll tell you what the 3 components of the electric field are at that point. And you could do that for all the points, and all of a sudden you have a nice, pretty graph of everything that's represented once again, okay? Any questions about that one? Before we do the last slide, which I have nothing hardly to say. It's just a different unit that you may sometimes see, and I want to make sure that you're aware of it. And it is the electron volt. 1 eV, the electron volt, is equal to 1.6 times 10 to the minus 19 joules. It turns out that a joule of energy, and we were talking at the start of the chapter about potential energies and dealing with that, a joule is really, really, really big. And we're dealing with things that are charged like electrons and protons. So often, instead of having to deal with 10 to the minus 19 on everything, it's just easier to re-express really small energies in terms of a different unit, like electron volts. It turns out that the electron volt is defined as the energy required to move a charge equal to the elementary charge, and keep in mind that's 1.6 times 10 to the minus 19 coulombs, through a potential difference equal to 1 volt. A, B, so in other words, if I had an electron and it was at one point and I wanted to push that electron over to another point that had a different potential that was 1 volt in difference, 1 electron volt is how much energy would be required to do that amount of work. So often when we're dealing with atomic things, electron volts are used for energies instead of joules, just because it's a little bit easier to work with, and some of your homework problems could have things in electron volts, and I just want to make sure you're aware of that, okay? We're done with all of this stuff for our test 1 week from today. So I want to do 2 problems by means of review. And let me just say in advance that if you've been working the homework, you might find it to be a little bit familiar. The numbers may have changed to protect the innocent. I don't know. But the problems may seem familiar. So if you've been working on it and getting stuck, you're about to get some help. If you've been working on it and got the right answer on problems that look like these, well, consider it just a review. Just sit back and enjoy it. If you haven't been working on the homework, get out. Just that's sad, it makes me sad, and you should be sad because you're going to be sad next Thursday. You need to be working on the homework, all right? So if you haven't been working on it at all, just take this as a little bit of a gift in the sense that like, oh, you're behind, you need a little help at this point. So don't just take the answers, make sure you understand all that I'm about to say. So let's go over and insert a new slide right there, right here at the end. Insert page, beautiful. Don't know why it never allows me though to insert a landscape page that matches everything else, and that upsets me. But one of these days I will sort out why the software will not let me do what I want to do. So let's see. Let me open up these files. For whatever reason, I didn't do this before class. Bad me. That's terrible. Let's see. Here. Nope, that's not the right one. Maybe this one? Ah, there it is. Okay. So let's start with a problem that looks something like this. Let's say that we have an XY coordinate system. And even though you will find something like this in the homework, I'm going to expand on it a little bit to help from a review perspective. And let's say that we have 3 charges. We're going to put a charge at the origin. We're going to say that that is positive. It is Q1. It is 3.2 microcoulombs. We're going to put another charge, say right about here. Let's call that Q3. It's negative, and it's equal to -4 microcoulombs. And then another one sits right about here. And we will call that Q2. And it is positive, and it is equal to 7 microcoulombs. Everything is in microcoulombs. We are going to say that these charges form an equilateral triangle that did not work out so well in my drawing, but you get the idea. All of these angles will be 60 degrees. The lines I just drew are not in any way physically there. I just didn't want to draw more dashed lines because it was going to look confusing. And each one of these legs of the triangle is 0.89 meters, at least in the one that I'm doing for you. And we're going to try to find a few different things. Let's just make a note over here. We're going to find, first of all, the electric force on the 7 microcoulomb charge. So the one at the top of the triangle. We are also going to find the electric field at the location of the 7 microcoulomb charge. Remember, force, you have to deal with both charges. They exert the same force on each other. Electric field is something that exists at a point in space. So I'm going to find the electric field coming from the other 2 charges at that point. And then finally, let's find the potential at that same location, at the location of the 7 microcoulomb charge. Force, field, potential. The 3 things we've been talking about all this time. So, first of all, that charge at the top, it is positive. It's going to feel a force from this positive charge in which direction? It's going to be repelled by that positive charge, right? So I could say that there is a force that points sort of this direction. And let's call that F12. It's the force from charge 1 on charge 2. F21 would be the exact same thing, just in the opposite direction. It's also going to feel a force from charge Q3 down here. Which direction does it feel a force from this one? It's attracted to that charge, right? So we could say that there is also a force that goes down this direction. I'm going to draw it just to keep things straight. I'm going to make this longer so that we have a little bit of room to work. Okay? So this would be force 3, 2. If I want to find the total electric force, I have to add those 2 vectors. So let's go ahead and step through that. So I'm going to break both of them up into components. So this one has a component that goes this way and a component that goes straight up. This angle is going to come out to be 60 once again, as far as I can tell. And then we will be able to find, let's see, this side would be F12 cosine 60, and this side is going to be F12 sine 60. Good so far? Yeah, I don't see a lot of confidence out there. Do you have questions? Got nothing, huh? Okay. Scaring me just a little bit. Let me change colors again. Let's talk about that other force. We can break it into components. It's going to have a component that goes like that, and a component that goes down like this. Let's see, what can we say about angles in this particular case? Any thoughts? Do I know either of the angles inside of that triangle?
Yes.
Which one? Where? All of them? Name one for me. So this is 90 here. Which one's going to be 60? I don't know. I didn't label it my problem for some reason. Which one? The one right by the 89? Is that going to be 60?
No. The one with the other two 60 angles.
Yeah. Okay, so we have a straight line up here at the top. So one way to think about this, this is a straight line, which means it's 180 degrees. And I already have a 60 and a 60, so the other one's got to be 60 to add up to 180. So that's one way of looking at this. So there's a 60-degree angle that's hiding inside there. So that means that this side is going to be F32 sine 60, and that other side up there will be F32 cosine 60. Finding forces is a good bit of work. So let's see. First of all, let's see if we can just find the magnitude of F12. The magnitude of F12, and then we can break that magnitude into components. We've already drawn the direction, so we have a feel for which direction that is. So this is going to be K, Q1, Q2, both of those are magnitudes, over R12 squared. R12 is that distance between Q1 and Q2. So let's see, if I plug these numbers in, I've got 9 times 10 to the 9th, and I'm very much running out of space on the side of this page. Q1, what is Q1? 3.2 nanocoulombs, or microcoulombs, so 3.2 times 10 to the minus 6. And we also have 7 times 10 to the minus 6, and we're going to divide all that by 0.89 squared. So I've got a magnitude of F12, and tell me if I've got a wrong number here, 0.255. If anybody gets anything different, let me know. That's newtons per coulomb. Yes?
Are you able to zoom in?
I can. Sadly, sometimes I lose some of the other stuff depending on, okay, we're good there. We're not good there. There we go. Okay, K, Q1, Q2, both of those need to be converted to coulombs, divided by that distance squared, 0.255. We can do exactly the same thing for F32. So that's K, Q3, Q2 over R32 squared. The only thing that's changed really is the charges. So I've got 9 times 10 to the 9th, Q3, and we're only looking at the magnitude, so that's 4 times 10 to the minus 6. Q2 is still 7 times 10 to the minus 6. And we've got 0.89 squared in the denominator. I have 0.318 for that. And I don't hear anybody complaining about these particular numbers. Maybe you're in agreement, maybe you're not. Maybe you haven't calculated them yet. Maybe you don't care. All of those are possibilities. So, if we want to find some components, we've already determined what the components will be. So let's write out these two vectors in component form, and I need a little more space, which means Let's try to keep as much of that around as we can. There we go. So let's see. If I wanted to express f 1, 2 in component form, I could write this as, where are these numbers? 0.255 cosine 60 in the x direction plus 0.255 sine 60 in the y direction. And for those two, I have 0.129 x hat plus 0.223 y hat, the two components of my force 1, 2 vector. And we'll do the exact same thing for the one between 3 and 2, okay? So force 3, 2 is 0.318 cosine 60. And it's pointing down, so the other one is negative, so 0.318 sine 60. And for those, I have 0.159 x hat minus 0.275 y hat. So we broke the two vectors into components, which means I can add the components back together to get the total sum vector. So I'm just going to sort of right here add those together. 0.129 plus 0.159 is 0.288 in the x direction, and these two are subtracted, and that's 0.052 in the y direction. So that overall force is to the right and a little bit down, okay? So we could use the Pythagorean theorem to find the overall force. So force net is the square root of 0.288 squared plus 0.052 squared, which is 0.293 newtons. And if you want to find the direction, we'll say theta is equal to the inverse tangent of 0.052 over 0.288. It's basically 10.23 degrees, and I put a negative sign in there to indicate that it's not straight right, but it's a little bit down. I'm going to try to go back up to the diagram because I want to draw something. Oh, I got to make it a little smaller. Okay. So looking back at this particular charge, the charge is sitting there. We now know which direction it's feeling an overall force. We know the components are to the right and a little bit down. And overall, we know that that little bit down is just 10 degrees down. So kind of in this direction, down that way, is where the overall force vector is pointing for that particular charge once I add those other two vectors together. So let's just pick a brand new color once again. What do I have left? I don't even know. Let's try this one, which you're not going to be able to see. Ooh, that's nice, right? So that is our overall force vector, ends up pointing kind of down that way. Good? So you drop the charge there. It feels the force from all this. It's immediately going to be pushed down and to the right with the force magnitude that we found. Anybody have any questions? Yeah.
What was the reason for why in the R10 you didn't add the negative to the 0.052?
You could, but we're kind of just solving a triangle at that point. Those are the two legs or the lengths of a triangle, and I want to know the angle. Anyone else? Thought I saw a hand, but I did not. So that's the hard part of the problem. It's a lot of work. Yeah. I am. Yep. I'll post, yeah, this is the end of these slides. I'll post the entire post-lecture. I don't know if you've been tracking, but I've been trying to, after each class, putting up something called post-partial. So even though we haven't finished the deck of slides, like there's something there so you can study with what we have so far. And I just delete that and replace it with an updated version. after we finish all the slides. So I'll get that done for you tonight. So we also want to find, let's see, the electric field and the potential. Now, if we hadn't just found the force, this next part would be hard. We would have to do all of this work to find the sum of the electric field vectors. But watch what happens. Remember, we have a different equation, right? We have force. I really shouldn't use this color, should I? What do you think? That's just the worst. Let's back that up and go back to something a little darker. So remember, we have force is equal to Q times E. Force is equal to Q times E, the relationship between the electric force and the electric field. The way this works, remember, is that the electric field is there at that position. I put a charge at the position where this electric field exists, and it feels this force, okay? So basically what I just found from above, this F net, this is the force on charge Q2, the one there at the top, okay? The 7 microcoulomb charge, all right? It is in an electric field at this particular point. So this is the electric field at the location of charge Q2. It's what I'm looking for. Which means that this Q here in the middle is just Q2. Okay? If I take the force that I just found and divide out the charge that's at that location, I'm going to find the electric field at that location, which means we're really close to done. So if I wanted to find E, it's going to be F over Q2, so that's 0.293, divided by Q2, which was 7 times 10 to the minus 6. And I've got 41,857 newtons per coulomb, and it points in the same direction, remember. It's a positive charge that we're dealing with at that location. It's going to have a force that's in the same direction as the electric field. So we'll say theta is negative 10.23 degrees. Well, that was nice. I really hope, and I've given problems like this on exams before, and people went through all of the work to find the force, and then I didn't make a connection. They did all the vector addition to find the electric field, and they just ran out of time because I never intended the problem to be worked with all of that work. You need to make sure that you recognize that connection between force and electric field. If you find one, you've got the other. You're just like one little equation away. Okay, force and electric field are that closely connected. If I want to find the potential, this is the one we're all enjoying at this point because it's just that easy. And we're trying to find the potential at the location of Q2, the one at the top. Well, don't think too hard about this. This will be the potential that's coming from charge 1 plus the potential that's coming from charge 3. So let's see, that is K Q1, whoops, we're talking to Siri here, I didn't mean to do that, over R12 squared, not squared, sorry, plus K times Q3 over R32. And those R's are actually the same. Remember, we're dealing with an equilateral triangle. So really, we could say this is just K over R. I'm going to factor those out since they're the same value, times Q1 plus Q3. So that's 9 times 10 to the 9th. R was 0.89. Q1 is 3.2 microcoulombs. And Q3 is negative 4 microcoulombs. Don't you love these colors? It's all really coming together. It's very googly at this point. Lots of primary colors. whatever reason, we're not gonna be able to see the bottom of that. I'm sorry. Try. I don't even have much room over there on the other side. You should get negative 80, 80, well, about negative 80, 90, interestingly enough, volts at that particular location. And look, this problem, that's all 3 chapters, at least parts of all 3 chapters in one. That's kind of nice. Throw in a little Gauss's law, and we've sort of got it all. You can't complain about that. Wasn't that fun? You're like, no, it was tedious. It was tedious, I completely agree. Way too much tedious there. Let's see, so to wrap up today's class, I want to do one more example, and I think we'll just stop whenever I finish it. Sound good? What if it takes longer than 20 minutes? It's not going to take longer than 20 minutes. You don't have to worry about that, okay? So let's see here. Let me get another slide, add a page there. And we're going to do one more example. Maybe you've seen this problem before, maybe you haven't. You will soon be able to tell me. Maybe you have been working on this problem and have no idea what the solution is. So congratulations, here it comes. Let's see, there is a half circle of charge, which is really hard for me to draw. So it's like a bar of charge that's formed into a semicircle, kind of like this. And it has some negative charge on it, like so. We are going to say that the overall length of this thing is 15.5 centimeters. It's just curved into the shape of a half circle, and yes, that's supposed to be half a circle. It's not really, but close enough. And we're going to say that it has a total amount of charge on it equal to negative 7.5 microcoulombs. So you'll look at that and immediately realize we could calculate a charge density, a linear charge density. We could divide Q divided by L and find a charge density if we wanted to. We're not going to right now, but we might later in the problem. And we want to find right at the center of this half circle the electric field. We're going to find the electric field at that point. So we can fill that out a little bit. So, remember, we find the direction of the electric field by imagining a positive charge and which direction it would be pushed or pulled. So if I am a positive charge here, and maybe I'm worried about this negative charge, what force am I going to feel from just a little bit of negative charge down here? I'm going to be pulled that way. But there's also some negative charge over here. So I'm going to want to be drawn to that. And there's some negative charge there, so I want to be drawn toward it. All of this negative charges, you can imagine, are giving me some electric field that's pointing in all of those directions, okay? So we could sort of start by saying, like, yeah, there's some electric field that goes that way, and some that goes down this way, and some that goes directly over here, and some that goes there, and some that goes there, and some that goes there. And this is starting to get ridiculous at this point. You get the idea. There's electric field at that point pointing out at all of those negative charges in all of those directions. So all we have to do is take this infinite set of vectors and add them all up. That shouldn't be too bad. Infinite vector addition. We're going to be here until probably Saturday morning. I think we can do infinite between now and Saturday morning, perhaps. I don't know. That's not an infinite amount of time, so we're going to have to find some symmetry here to help us out a little bit. So at first glance, looking at these vectors, notice like this one and this one, they're going to cancel out. There's an equal amount of negative charge at the top and the bottom. If I were to say maybe look at this vector and one that sort of goes down this direction at the same angle, well, it's going to have a y component that points straight up, and this one will have a y component that points straight down, and those will cancel out. So for every vector, there's always going to be a y component at the top that cancels with y components at the bottom. But at the same time, every one of these is going to have an x component with nothing to cancel it out the opposite direction. So all of the x components are going to add up, and all of the y components are going to cancel out. So y components cancel, and x components add. Y components cancel, x components add. So the electric field in integral form, let's give ourselves a little space here, is equal to k times the integral of dq over r squared. But we want to just have the x component of that. So E, we'll say E total is going to be the sum of all the x components of the electric field, which we could express as k times the integral of, say, cosine theta dq over r squared. That cosine theta is coming from the x component, okay? If I were adding up all the y components, I would throw a sine theta inside there to indicate that I'm trying to find the vertical component. So we can make some substitutions here. You notice right now we've got r, theta, and q all hiding inside that integral. That's not going to help anybody else to do any calculus at all. So we could first of all say that lambda is equal to dq over dl. A linear charge density, it just happens that our lined charge has just been shaped into a curve this time. It's still all not spread out along the surface. They're all just sort of in a row. So we could rearrange that and say that dq is equal to lambda dl. And this little bit of length is just a little piece of this curve. It's an arc length along a circle. So I can re-express that as r d theta. A little bit of arc length is equal to the radius times a little bit of the angle. And we're going to plug that in for dq. And then we've got those things in terms of theta at least. So let's see, let's go to the next level. I can take that r squared and pull it out because it's going to be a constant value. So I've got k over r squared times the integral of the cosine theta that's already there. And now I've got lambda r d theta. Plugging in for dq. Lambda r d theta, the cosine theta was already there. Pull out the r squared. So both lambda and r are both constant values. So let's pull those out. So now I've got k lambda r over r squared times the integral of cosine theta d theta, and that's something we can integrate. So we've got an r there that's going to cancel, and then we'll do the integral. We're going to integrate from negative 90 degrees to positive 90 degrees. We're doing that because we want to go from here at the bottom, assuming 0 is in the middle, we want to go from an angle all the way straight down, negative 90, through 0, and all the way to the top to make sure we add up all of the pieces of charge. So let's see, we're going to cancel this r with that one. So now I've got k lambda over r, and this becomes sine theta, and we'll evaluate that from negative pi over 2 to positive pi over 2. And that looks like it's starting to agree with what I have there in the answers. So now I've got k lambda over r, and let's see, we're going to have inside here the sine of pi over 2 minus the sine of minus pi over 2. Just add a space over there. the sign of that is just 1, and this one is -1, but I also have a negative sign out front. So that means I'm going to end up with 2 times k lambda over r. 2 times k lambda over r. We can make one change to this, and this change would actually allow us, see these numbers they gave us at the top? They gave us L and they gave us Q. Ugh. I don't have L or Q in this answer. That's a problem. I've got lambda and I've got R. So if there's a way for me to re-express lambda and R in terms of the variables they gave me, then I can actually get the numerical answer that they're looking for. So let's see what we can do with that. So first of all, if I were to form this into a full circle, that would be 2 times the length. So it's half a circle, so just 2 times would wrap around an entire circumference. So that would be equal to 2 pi r. So the 2's cancel out, and we could say that r is equal to L over pi. So let's plug that in here and see where that gets us. So now I've got 2k lambda, and we've got an r in the denominator, so that's going to give me pi over L. So I'm a little bit closer. The only thing that's still in there that I don't have is lambda. So if we could do something with lambda, we'll be in good shape. So let's see. Lambda is equal to Q over L. It's our charge density. So let's plug that in. And now I've got 2k q pi over L squared. I have a value for L, I know pi, I know k, that's our constant that we use for electricity. And Q is a number that's given at the top. You can punch the numbers in and see what you get, okay? But that is the algebraic expression of the answer. Congratulations, I just did 2 of the homework problems in chapter 22. So if you haven't started working, there's at least a little bit of a jump start for you. If you have started working, congratulations. I hope I just confirmed the answers for you, gave you a little bit more practice. We'll see. So 7, 8 minutes early, is that good enough? You want to do 8 more minutes of stuff? Wow, you're already walking out. I take that as a no. You are leaving. Bye. Have a good weekend. Yeah, that is the definition of linear charge density. It's like if I have a bunch of charge standing up, I take all that charge and divide by how much sleep is spread over. It's, we covered that in 2 or 3 linear charge. Yeah, I think yeah, it's like all of those. Anything else you're bothering? Yeah. Yeah, but the thing that's giving the potential here is these bugs of charge. So I'm trying to find out all it's almost like this is not trying to work it out. It's almost like I have charges that are like let's go by it. Like this. And when I go out here, I need to calculate that.
I'll let you know about tomorrow because I do have to do here. 2, 3, and then I might just for that.
It's always that. Using largest stars. It will, well, if I'm in a loop like this, imagine just sort of rotating that around. Always be the exact.
Bro, I worked in the morning, opening for 7 to 12, I think. I was chilling, I was just laid out, like refresh my head before I went flat. And at that one, I was at 7.
Yes.
I was like, oh shit.
Yeah, the last problem we did, let's pull that back up, just to make all of our lives easier. Yes.
Right here on data is a bit just point in with a radius within one added distance.
It is, if I have a little bit of arc here, this is S equals R beta.
Alright,
That's what we're using, just in,
I know I'm
yeah, totally. So
so it's the same thing.
it's the exact same thing, just S is that we're using.
I started.
Yeah. I think you are. As long as you're not just misspoke. Does that answer your question, you think?
Yeah, I talked to him today, he said.
Yeah. Great. Thank you.
I was actually gonna ask the same
Same
question.
thing.
Yeah.
Work length.
Are we gonna do another review and?
Tuesday, we're just going to spend the whole time doing review problems, and I'll try to also sort of present an overview so you kind of see what all the material is, maybe a little bit. But if there's anything you want me to address specifically, send me an email. Okay? You're welcome.
It's so much easier. I have to figure it out.
Yeah, doesn't it? It helps, doesn't it? I completely agree.
Because I've been taking